All right, I think we will begin now. Yes, so good afternoon, everyone. I am Yashima Jain, and I will be moderating today's webinar on heat transfer and your building envelope. This is the second technical session of the 10-part webinar series. Next slide, please. So before we begin, I would like to acknowledge the support of our sponsors and affiliates. Next slide. Now, today's session is being conducted by Professor Rajan Rawal. Professor Rawal is a CRDF professor at CEPT University and the Executive Director of Center for Advanced Studies in Building Science and Energy, also known as CARBSE, at CEPT Research and Development Foundation. His work emphasizes on energy performance of human habitat, thermal comfort, and architectural science education. Professor Rawal is also on the group of advisors for Solar Decathlon India. We welcome you, Professor Rawal, today. Now, before we get into the session, let's go through some administrative stuff. First, we hope that most of you have got a chance to review the self-learning module on heat transfer. Now, also we have been receiving a few queries regarding the Design Builder software, and in order to get access to the Design Builder software, we request you to share information as mentioned in the declaration form by us. Only then can further details be processed for you. And lastly, as always, you are free to send in your questions at any time during the session. We will take as many questions as time allows during the session and provide answers to the remaining questions. Please remember to type your questions in the Q&A window and not the chat window. And with that, it's over to you, Professor Rawal.
Thank you, Yashima. Thank you very much. And before I begin, let me congratulate Indian Institute of Habitat Settlements and IEEE for starting this wonderful initiative in India. And special thanks to Professor Prasad Vaidya and Dr. Satish Kumar of IEEE. I've been assigned to talk about heat transfer in buildings. What I'll do is I'll try to take you through some basics and then show some examples, trying to help you out what should be the construction assemblies and what should be the materials. That is what I will be spending about another, 35, 40 minutes or so. But before I begin, I want to give you a small story about how Igloo gets built. And the reason I want to tell you this is an example where not just a material, but how materials is been put together for the benefit of indoor thermal environment, and the whole process which involves, in a manner, very rudimentary technology, but other way around, if you see, it is pretty sophisticated in a manner the way the whole process takes place. The material is, as all of you, as you know, that it's ice. Ice blocks gets formed, and then slowly the dome will get formed. In fact, first layer of the ice blocks, first they place it and then they chamfer it in a manner so that it becomes little cyclical, and then slowly they will build the entire igloo. Now, when they start putting these ice blocks, what happens is that since it is not very fine cut ice blocks, they use hammers and axe to shape them. Definitely, that means that the edges of the ice box will not be very sharp. And when you put one ice box on top of another, there would be some kind of air gaps. And that air gaps might harm the way you want to sort of retain internal heat. what they do is that once they put a sort of capstone on top, and once they make the entrance part, they will close the entrance part and they will close also the capstone, and then they will lit a lamp inside. The lamp primarily would be the fuel which they use is a fat of a seal, which burns and slowly creates a warmer environment inside. This warmer environment impacts the ice, and ice starts melting a little bit. Once it starts melting, it forms a sheet of water on top of these ice blocks. And the moment, and one or two people would be inside observing that how this water sheet is getting formed. Basically, water will start melting and it will start slowly coming down. The moment they see that water sheet is sort of complete, they will open a capstone or cap ice blocks and an entrance, and then they let the cool breeze come in. That cool breeze immediately freezes this water, and that also makes the igloo sort of airtight. This is a very unique process which they follow the same material. And if you put it in today's term, you have a brick made out of clay, but your mortar is also clay. And that's how the whole homogeneous construction takes place. And instead of making a sort of barrier from outside to inside, this whole thing works more like a sweater or any kind of pullover, that it helps you to retain your internal heat. And that's what the story of Igloo is. With that introduction, probably I will sort of revisit those three heat transfer principles. I am aware that SDI organizers have given you self-learning modules, and you would have gone through what is a conduction, convection, and radiation in a buildings. But just to have a little bit of recap, conduction takes place when you have certain amount of material available. So what you see on the left-hand side, if the surface temperature is higher on T-surf1, which is higher than T-surf2, the heat will transfer from one point to other point, or one phase to other phase. Versus if you have a surface of any material which is at the higher level, and if the fluid like air or water has a lower temperature, this fluid will try to take the heat off the surface, and that we call it sort of convection. Through the movement of the fluid, the matter try to lose the heat. And in a radiation, what happens is that two surfaces comes they start based on their surface property, whether it's emissivity or reflectance. It will start sort of interacting with each other and will transfer the heat. That's a little complex way of looking at it, especially indoors of the building. The outdoors, we definitely know that how our roof or our wall works with the radiation. Again, if you turn that into a simple example, if you have a hot block and if you have a cold block, both one at hot block at 30 degrees centigrade, cold block at 20 degrees centigrade, and if you place them next to each other, touching each other, over some period of time, although it's difficult to figure it out how long will it take, but at some period of time, both blocks will try to attain same temperature. Versus when you are looking at a convection, really hot side, which is 50 degree, cold side, which is 20 degree, and if that has air inside, or rather moving air inside, the air will try to take the heat off from the hot block and will try to transfer it to the cold block, and ultimately both will attain certain amount of, same amount of temperature. Similar way the radiation works, as I mentioned earlier, it's a surface property which comes into the act. Now, when it comes to heat transfer in buildings and what kind of influencing factors we have, it is very important to segregate these two into two beams. One, because it is such a complex process that whether you want to, if you want to understand the design of a building, elements of the building and heat transfer happening or heat transfer interaction taking place in various architectural elements, that's one way of understanding that. Another way of understanding is through the materials and construction. So generally what I try to do is I try to place them in two separate baskets. One is where we call it an influencing factor because of the spatial design characteristics, such as geometry, whether it's a cuboid or it's a dome. It's massing, whether you have certain high mass on one side or low mass on other side. Orientation of the building, whether your longer axis is oriented towards north-south or east-west, that will have an impact on heat transfer. And also surface to volume ratio. If you have a simple cuboid versus if you have a cuboid which has many facets inside, almost like our bike's engine or any two-wheeler's engine, where you will see a lot of fins. So heat transfer within the building also, like for example, a building with a lot of facades and balconies and stuff like that probably have a more surface, higher surface to volume ratio. It will act differently than simple cuboid building. Again, where these will act, it's a different case, but we are just irrespective of climate zone, we are trying to understand what are these special parameters. Extent of fenestration. When we say fenestration, we try to look at three things together: window, doors, and skylights. What is the sizes of the window and what is the characteristics of it? That comes into the picture. Internal volumes also, if you have a smaller volume, if you have a higher volume, and if any kind of stratification taking place inside these internal volumes, and static effect that is taking place, probably air will start moving from bottom to top and you may try to reject the heat. It also can take place, not necessarily all the time, can take place if you have buildings which have a courtyard. Or sometimes location of fenestration. Either you put it two windows on two opposite directions, or you put it little differently. That also will help you to reject or gain heat, depending upon where you are. Versus if you start looking at material and methods, the thermal properties of material will come into the picture, whether it is a brick or it is an insulation. But not only that, how the brick is laid, how the same material, brick is a sort of component, but how the clay brick is been laid in construction also make a difference. So one brick thick wall versus two brick thick wall will have a different kind of thermal characteristics. A brick wall with the rat trap bond or a brick wall with a cavity inside will have different kind of, all the material is the same, but how you are laying it for the wall will decide what would be the heat transfer through these walls. Similar way for the windows. Where are you placing this window? One is a spatial design. Where you are putting is, I would say it's a spatial design decision versus how are you putting it and what is the construction of that, what kind of frame are you using, what kind of glass are you using, is where the construction and material comes into the picture. So what I have done is very quickly, I want to show you although everything is related with each other. But if you have to, for a while, if you have to slice it down, that where the convection is, where the conduction is most important as far as the wall is concerned, probably the materials and construction method is very, very important when you start talking about wall and conduction together. But when you are talking about wall and convection, probably it is sort of a neutral. But again, wall and radiation, and especially construction materials and methods, as I was mentioning that for radiation, the surface property of the wall will matter. It's not very, very important to focus on. When it comes to fenestration, does, the importance of fenestration is very much there when you talk about convection, conduction, and radiation. And in sort of, it's also very high, primarily because the material we use for a construction, for the construction of fenestration is such a material where it has a high impact on conduction, high impact on convection and radiation also. When it comes to roof, surely the radiation is most important aspect which you need to look at. I'm not sure whether you can differentiate two red color on your screen. One is a darker red color and one is a lighter red color, where I'm saying that this is very important. This is not very important, or rather important. But probably the slides or the soft copy of this, when SDI administrators will circulate you might be able to see two colors a little differently. Now, how does this connect with climate zones? Again, as I'm saying, and I repeatedly wants to say this, that please don't take these as a rule. These are just an indication where you need to focus on. As you know, in architecture, in engineering, many things are, sometimes they work, sometimes they don't work, depending upon the context. So you need to take your own judgment before you say that this is what we are doing. My intention here is to show you that where is a higher importance and where is a lower importance. If you start looking at these 5 climate zones which are prescribed or identified in an energy conservation building code, the hot, dry, warm, humid, temperate, composite, and cold, what I have tried to do is that geometry and massing, which is more spatial characteristics or spatial design decision, will become very, very important when you are looking at warm and humid climate. Primarily because that's where your orientation of the building needs to take advantage of prevailing wind conditions. In hot and dry climate, it also will matter, but not as much as a warm and humid climate. To me, if you ask, and this could be debated very well, but if you are looking at hot and dry climate, you might want to put a little bit more emphasis on a construction of the material along with geometry and massing. So construction of material comes first, and then probably the geometry and massing. But when it comes to a warm and humid climate, you might want to look at geometry and massing more importantly than just a material. Anyway, let me move forward. So when you talk about external surface to a building volume ratio, again, in a conduction, it will start mattering. In a warm and humid climate, it will matter a little less. So this is the way probably you can start your design. This is not the way you can end your design, but this is one way by which you can say, let me put a little bit more efforts, let me put a little bit more emphasis on selection of material on one side and design decision on other side. I'm sure that there would be a lot of questions which would be raised based on these 2 slides which I showed right now. Now, what will matter, and in terms of units or in terms of thermal properties of a material, and this is where I have tried to put at least 3 elements. Wall, we are more talking about external walls than internal walls. Fenestration, and again, focus is more on windows. And on a roof, it's more about roof and not really floors and stuff like that. So in a wall, material thermal conductivity and resultant R value or U value will become more important. If you're looking at thermal mass, and I'll talk about this a little bit more later on when I talk about mixed mode buildings, But if you are trying to operate your building in a manner where some point in time you are using air conditioner, rest of the time you are trying to use natural ventilation, provided you are in that kind of climate zone, then you might want to look at the thermal mass and a specific heat of a material. When it comes to fenestration and windows, as you know that radiation, convection, and in fact a visible light also becomes important. So you should be focusing on R value or U value, which basically a frame and a glass panes, solar heat gain coefficient, and visible light transmittance. All these three becomes very important when you start looking at windows. And when it comes to roof, fortunately, you just need to look at the surface property to start with. Again, if surface property, and if you can retain lower surface temperature, you are better off. But lower surface temperature, but then you have very high conductive material like a steel, then probably it might not help you that much. So, but still, the surface property is more important when you start looking at the roof, and hence the emissivity of the roof and surface solar reflectance of the surface is where you should concentrate. How orientation impacts, and again, this is a very simple way of putting. What I have done is I have taken about 1500 square meter building in a hot and dry climate. And what you see in the first graph is your aspect ratio is 1:1. The red where you see aspect ratio is 1:2. But one point in time it's placed on east-west longer axis. The third column is where it is the north-south longer axis. And in fourth and fifth, the aspect ratio is 1:3, but the longer axis is east-west and longer axis is north-south. So if you have this, what will be your annual energy consumption? Probably your consumption may start rising because in 1:3 aspect ratio, the wall of eastern side and wall on a western side will receive a lot of solar radiation, and hence there would be a higher heat transfer. And as you can see in the next graph also, that during the summertime, you will have higher gains per square meter. And now, similar kind of approach if you start just looking at window to wall ratio. If you have first bar where you have 20% window to wall ratio, second bar you have 40%, third bar 60%, and fourth bar 80%. Now, if you are a business as usual building, looking at business as usual building, probably what may happen is that since the fenestration is a sort of a weak link between outside and inside, there will be a lot of heat transfer. The moment you start looking at ECBC, that means your solar heat gain coefficient, your VLT, your R value of material, window or fenestration would be much better than what you see on a business as usual case. Immediately your heat transfer will come down. So your cooling load will drastically reduce. And what I'm presenting here is one side, first two are east-west, next two bar graph are for north-south. Again, you can see how orientation and WWR and BAU versus ECBC, how does it really fare with each other? But what is very interesting here is not just a sizing down, but also variation in it. As you can see, business as usual, 4 window to wall ratio, delta between two cases is very high. But the moment you become a more efficient, moment you start reducing the heat transfer, even with the 20 WWR, 40 WWR, 60 and 80, the delta between these four will start reducing. And this is where the code makes a lot of sense, where you start looking at a high performance of fenestration and design and construction both. What I'm showing you is impact of shade. Again, in the first, where you are looking at business as usual, but the moment you put ECBC code compliant, you can put ECBC plus and super EBC, you can see the large variation between first and second, but not so much of variation between second, third, and fourth, because once you attain certain amount of resistance, or when your window becomes sort of high performance or better performing, then difference between ECBC, ECBC plus, and super ECBC might not be very high. When you are going to look at the net zero building, this is where you need to find a sweet spot, because I think competition also requires you to show certain kind of cost benefit analysis. Will you really go for super high performance glass or high performance window, or rather super ECBC at 3 times more cost? But it may save a little bit of energy as compared to ECBC. So this probably you might need to look at where the sweet spot between energy saving and cost, and now also renewable energy generation. This is where such kind of analysis might help you. What you see on the right hand side is again business as usual versus reduction or savings in a cooling load if you have a 300 mm, so that is about a feet or so horizontal projection, there are 2 feet of horizontal projection, and again combination between east and west and north and south. So just trying to show you the way various parameters needs to be dealt with individually to start your design process. But at some point in time, all these may become very, very complex. You might get confused that what is to be done. It will happen, and it should happen. Then and then you will be able to take a good informed design decision. So what may happen is that I have drawn sort of 5 lines here. In a first line where somebody is trying to look at the orientation. In second line, somebody is trying to look at the U value of the wall. In third vertical line, you are looking at 2 kind of overhangs, 1 feet, 2 feet. Then you are looking at window sizes. And then finally, probably what you are looking at is RETV value. Although RETV value is not very much part of the ECBC commercial, but if you are looking at residential buildings, the residential energy transfer value may become important to look at. Then what you can do is that looking at the cost benefit analysis or looking at the savings, you may pick up one path, the way I have described in a black dotted line. So let me go for east-west orientation. Let me go for a U value, which is probably the U value of the wall, sorry, U value of the window, which is about 2. Then I will go for a 0.3 overhang. Then my window sizes could be 1.2 or so. And then probably my RETV may become about 15 or 16. This is how you may take, so you might want to look at a design builder and multiple runs before you arrive at, okay, let me start taking all these 5 or 6 parameters together and take a design decision. So that's the one way of looking at it. What I'm also showing you is an output of a small tool which might be available with you guys as well, where impact of the shading. Shading is one of the most cost-effective way of protecting your window and achieving lower heat gain coefficient or high performance windows. So what you're seeing is on the x-axis of each of these graph is 1 day. So 1 pixel or 1 row shows you 1 day, and from 0 to 24 is hours. So all those black hours which you see are nighttime. As you can see, middle of the year, you have a more sunshine hours, so that the whole thing becomes a little broader. And if you don't have a window, you will have all these red. So your solar heat gain coefficient could be 0.6, 0.7 or so. But moment you put a shade on top of it, a simple horizontal shade, your solar heat gain coefficient drastically reduces in the range of about 0.4 or 0.3. and depending upon where the sun angle is. ECBC just have one value. You need to hold on to that value only. What I'm showing you is SHGC which varies during the day and during every hour. What you may need to demonstrate in your design competition is that the one single SHGC value and not hourly values of that. And that is what you see the last one, the difference. The last bottom one is showing the delta between first and second. And as you can see that very much has been achieved during the summertime when you have simple horizontal overhang. This is now, if you can correlate this with the sunpath diagram, why do you have a maximum impact of horizontal shade during the summertime? If you start investigating, you will realize that during the summer in India, and especially in the places like Ahmedabad, this is a graph from Ahmedabad, your altitude of sun is much higher. It's more on your head. So a little bit of shading on your building will cast a long shadow on the vertical surface, and hence that is how the solar heat gain is improving during the summertime when your altitude of sun is very high. So this is one example how you can do the analysis for your overhangs. Let me shift towards wall as well, and I will try to explain you how do you really deal with what is the thermal insulation, and how do you really deal with thermal insulation and a specific heat. Thermal insulation it helps us to prevent transfer of heat. That's how you put it. It's sort of insulation which does not allow heat to come from one side to other side. It's almost like a raincoat, where if you wear a raincoat in a rainy day, your skin will not get wet. Versus thermal mass is where the specific heat, probably there is a typo here, instead of thermal insulation, it should be thermal mass in the second picture which you see here, is like a Kambal, is where heat will penetrate inside. But because of the high mass, it will not reach other side. So what happens in a Jaisalmer Haveli, where we say, oh, the internal temperature remains same, that's because of the thickness of the stone wall, where from outside heat will come in during the daytime. And as you know that heat will transfer from higher side to lower side. So lower side is the inside temperature is low, higher side, outside is high. Heat will start coming in, but before it reaches the internal surface, outside temperature drops and heat will start going out. And that keeps happening because of the thick stuff. The internal temperature doesn't go up. Very similar to, let's say, if you, in the rainy day, if you wear a very thick kambal, what will happen that the cotton of the kambal will get wet, but it will not come until your skin. Hence your skin may remain sort of less wet, I would say. So this is how probably you can use a thermal mass and thermal conductivity. Keep one thing in mind, that both of them have an advantage, both of them have a disadvantage. When you are putting insulation, it is not allowing outside heat to come in. But if you are generating heat inside, if you have a lot of computer inside, if you have a lot of people inside, if your internal load is very high, it will not that heat to go out. Now, what do you do there? Probably you might want to rely on convection. Right now, what we are talking about is a conduction, where through the wall, you are not letting heat go out, you are not letting heat go in, but you know that windows are operable. And through convection, you can lose heat. So let's have insulation on a wall or high thermal mass wall whenever we want to manage the internal temperature, and if outside is favorable, probably we can open window. So there is a bit of operability also comes into the picture. as an architect generally, or even a civil engineers, even a mechanical engineers, we don't try to look at the operation so importantly. We just try to design. But Solar Decathlon and India and also net zero is where you need to put enough thought on how are you going to operate your building, not just a design. How are you going to operate building? And that's where you might need to stretch yourself a little bit more. A little bit about insulation. What is that? It's basically you try to reduce the heat transfer. Number of ways you can do heat transfer. You can reduce heat transfer is either you create a very porous material of air, which is of very, very less conductivity. You try to trap the small bubbles inside and reduce the conductivity of material. So you reduce the mass. What is the sort of comparison between these two? As you just observe this, although I'm showing you various material here, but the x-axis is a logarithmic axis. It's not a linear. So aluminum transfer a lot of heat as compared to adobe, as compared to clay brick, as compared to aerated concrete, and as compared to mineral wool. Huge difference. Now, when you are putting an insulation on a window, or sorry, insulation on a wall, as I was mentioning earlier also, the construction method becomes very important. How are you putting it? It is not what are you putting it. It's what are you putting it and how are you putting it together. Now, as probably you can see, here is a tag board, and somebody might have put a sheet metal screw to fix this tag board. Now, sheet metal screw is high conductive material. What you're seeing on the image towards lower side is a thermal bridging. What is thermal bridging? Very simple way if I want to explain that. If you go to kitchen, if you want to warm your milk, you take a stainless steel bowl, put on top of the LPG gas stove, start warming. But if you want to stir it, if you are putting a sugar inside, you may want to stir it. When you stir it, and if you keep that spoon inside, next time when you want to stir it again, and if the flame is on, you will not be able to touch that. That's where the spoon is touching the bottom of the bowl and transferring heat very quickly. Hence, what we do is that we put either the spoon next to the bowl or on the platform, or we use a spoon which has either wooden handle or a plastic handle or something else, which is a low conductive material. So when you put a screw on the insulation is trying to reduce the heat transfer, but the screw with a super fast heat flux will start taking heat out. The comparison is that if 1 square meter of insulation is equivalent to 2 square centimeter of aluminum, so amount of heat which can get transferred from one side to another with a 2 square centimeter of aluminum sheet will nullify the impact of insulation. So I'm not sure how much do you need to show the construction technology in a SDI, but I'm sure that Professor Prasad and Satish might have thought about it and might ask, or you might gain a little bit more if you show the construction technology, not just specifying that we will put insulation. How are you going to put insulation also may get you a little bit of more marks. Comparison of insulation. Let's say if you have about 200 mm thick brick wall, which is equivalent to about 100 mm cellulose insulation. It's about 75 mm thick XPS insulation. And probably you can go down to say 10 mm, 1 centimeter of vacuum fiberglass insulation or vacuum insulation. So that's the way probably sometimes you might want to save some space, but make sure that you decide the level of insulation in your building. It can cut both ways. It will not allow heat to come from outside, but it may retain heat which you are generating inside. So where do you put the insulation? The next couple of slides is where I'm trying to show you that if you put insulation outside, the outside surface temperature and the inside of the, this is what you're seeing is a wall section. Inside of insulation, you may see drastic drop in a surface temperature. Then you have a brick or concrete and then it'll go in. But if you put insulation inside, the heat all will penetrate up to the inner side of the concrete and then you will see a drop. Now, if you are having an air-conditioned building, you may not want to lose heat. You may not want to even cool your wall. In that case, you may put insulation inside. But if you don't have a completely air-conditioned building, you may wish to put it outside as well. And when you have a high thermal mass, as I was mentioning, a Jaisalmer, you might want to have a thickness. You want to use a specific heat of the material to keep absorbing heat. And then you rely on outside temperature difference to reject the heat back. Sorry. Where sometimes in a colder climate, so the earlier slide which I showed was for hot and sunny climate or hot and dry climate. This slide is for cold climate. If you put the insulation inside, you might want to place a little bit of more efforts understanding whether condensation will take place between two layers or not. If condensation takes place, it's a little bit of, if you don't have a vapor barrier, probably the effectiveness of insulation will reduce. So depending upon climate zone, you might want to decide where you want to put insulation. If you are built up, all these, what I was suggesting, that your internal air temperature, you are retaining in a same sort of band, versus if you are not maintaining internal temperature in a very narrow band, you may sort of want to rely on something which is a combination of insulation and thermal mass. These are 6 examples of six kind of construction where it shows that outside surface temperature and inside the surface temperature. So what you're seeing is the first dot is outside air temperature, then outside surface temperature, then inner side of the material, then you have a cavity, that is the first slide, first image, and so on and so forth. Why am I showing you this is that just look at the U values of these, especially the second one and third one, where U value is the same, but still the surface temperature is varying. That is primarily that the cavity inside, you have a 4.5 inch thick brick wall, you have about 50-60 mm of air gap, and again but the air gap in one of the case is ventilated, in another case it is not ventilated. So again, how your cavity is functioning will matter. Very quickly, I'll probably go, maybe I'm running out of time, that looking at the glass. When it comes to glass, you may wish to look at the wavelengths in a solar range versus transmittance of heat. There are certain kind of glass which has a better way of managing visual light and also managing a heat which is coming in. So they're spectrally selected glass. They do let light to come in, but they do not let heat to come in. And you will get these kind of database from, again, there's a last slide where I'll be showing about where you can see that, what kind of glasses are available and what is the range of their spectrum would be available. So if you see that on x-axis, if you put a solar heat gain coefficient, on y-axis, you can put a visible light transmittance. It is very difficult to get a glass which has very low heat gain and very high VLT. That is what we want. We don't want to gain heat, but we want to see a lot of light. But to manufacture that kind of glass is a little tricky or difficult. Most of these glass use silver as a material to manage its spectral selectivity. So what you see generally in the market is either glass has a very low VLT but very good solar heat gain coefficient, or very high VLT but middle or little less or higher solar heat gain coefficient. Again, there are 5 kind of glass has been compared here, that how various kind of glass, what you see is the code number of the glass or product number of the glass, how the reduction in a cooling load takes place depending upon a selection of the glass. Not only glass, but window also makes a lot of difference, because glass may be a U value of a glass, maybe, or it's a weak point where a lot of heat transfer will take place. Even double glazed window, double glazed assembly, you will have a lot of heat will take place. But also, sometimes if you have frames which are made out of high conductive material, more heat transfer may take place from window than a glass. So what you need to look at is you need to look at the glass and a window as a complete assembly to start looking at the performance of that. There are certain kind of windows available which are thermal break windows. That means on one side is aluminum, other side is aluminum, you have a double glaze, you have a triple glaze, but in between, when it's a very low conductive material, as you can see in the middle of the slide, the picture, that is made out of sort of PVC kind of material. So the one side of aluminum, other side of aluminum has a break, has a thermal break in between, and that doesn't let the heat transfer or less heat transfer through the window frame. This is sort of important to look at, that don't just look at the glass, but look at the glass and window together, glass and frame together. It's not that, although on the left side you see how a single glaze window, what will be the U value you can achieve, about 5 or 6, but to start making a double glazed windows with argon feeling, without argon feeling, with the low emissivity glass, which is sort of spectral selected, your U value will start coming in. But on a right-hand side bottom, where you see the position of the window, position of the pane, if you have a vertical, same assembly may fetch you probably about 1.1 U value. But if the same assembly is placed like a skylight, probably U value will go up to 1.7. And if the same assembly is placed horizontally, then it may have about 1.7 of U value. This is primarily because the internal air current and the speed of movement of the air may increase when you put it horizontally versus vertically, and hence it might create some kind of internal convective currents and starts transferring the heat from one place to other place. 2 examples here. This is one of the building in CEPT University where we operate our lab is. The building is sort of net zero. How it becomes net zero, probably next slide will help us to understand, but the building is getting operated in various modes, and primarily 3 modes. The air conditions, when outdoor is very, very harsh, we close our windows, we operate with the air conditioner, high efficient air conditioner. When outdoor is favorable, we open the windows and we let cool air come in, and we do not operate air conditioner. Sometimes we may operate only fans and try to gain a comfort. Again, this is the kind of assembly which we have used in the net zero building at CEPT. Because of the aesthetics of the CEPT needs to be maintained, outside is a 4.5 inch thick wall made out of brick. Then we have an XPS about 50 mm, then 230 mm, which is high thermal mass inside, and then a plaster. Depending upon where you are, the first floor has a different assembly, basement has a different assembly because basement has a concrete walls, has a retaining walls on the side. Similar way on the roof, we have a waterproofing, then we have RCC waterproofing, and then we have a foam PUR, which is a single piece insulation from one end to other end. But for intermediate floors, probably the floor which you see an intermediate, which is a naturally ventilated floor on the ground, does have assembly which you see on number 3, because it is in a manner exterior floor for first floor, and hence the insulation was kept on the soffit of the first ground floor, makes it sort of external insulation. And how does it operate? You can see outdoor air temperature going up and down, and you can see the surface temperature of window is it's really damping the surface temperature of that is very low. We're using a low E glass there and also double glazed windows. And when you start this is basically environmental parameters, surface temperatures, which I'm showing you right now. And then when it comes to energy, on the upper side, which you see a yellow, is where outdoor temperature going up and down. The black is indoor temperature, and it drops down whenever there is occupancy. It goes up a little bit in the nighttime when people are not occupying. The red graph which you see is a electricity generation through the photovoltaic, and then amount of energy which you use. The blue in a summertime is which shows a very high consumption from HVAC, and depending upon how many machines are we using, we are not using, it shows you a HVAC consumption. And sort of last slide is where there's one of the building in Orville, a Blessings House, where we were working to monitor with one of our colleague, Mona Doctor, and it's a very small house, 4 rooms, 2 rooms on the ground floor, 2 rooms on the first floor, but very innovative way of managing thermal mass and insulation. Outside it has aerocon blocks. That means it's a low conductive material. Inside is a compressed earth block, which is having a very high specific heat. And combination of these two, what happens, what you see on the right hand side is the black line shows us window open and window close. So during the daytime, window remains closed. During the nighttime, the open window, or rather, at least for this experimental period, we managed to do that. So what were we trying to understand is that during the nighttime, when outside temperature is low, you flush the cool air from outside and charge your internal thermal mass. And when outside temperature starts going up, you close the windows and you start using the insulation of aerated concrete block to keep the indoor surface temperature down. So what you are seeing here is that the yellow line where indoor temperature remains in a very sort of on a flatter line versus outside temperature goes up. This is where not just a construction, not just a material, but material and construction. How are you placing, where are you placing, and operation of your building. Are you opening window? You're not opening window. When are you opening window? How much are you opening window? All that comes together. So this is a very brief sort of example which I wanted to show, showing the importance of construction, material, and operation together. These are some of the resources. There are a lot of online tools available, a database available. I'm sure that the SDI team must have shared many other websites with you, but I thought probably I should share this as well with you. So let me stop here. I have really taken a bit of time, but I can compensate that by staying a little longer. Thank you.
Yep. Thank you, Professor Rawal, for this very insightful session. And I hope our Solar Decathlon India participants will now be able to think more effectively about heat transfer for their project and design their building envelope to reduce load and increase thermal comfort. And with that, we'll take questions now. We've had a lot of questions coming in. So the first question here is how to use creepers on the facade to reduce thermal heat gain and at the same time maintain sufficient daylight inside the building.
How to use creepers on the facade?
Yes.
I think the question itself has an answer that how it will reduce the heat gains. And so let me try to sort of put it a little differently. Why does it happen? Why does it do what it is doing? So basically, your solar radiation falling on the facade will get absorbed by this vegetation. And the thumb rule which we use is about 50%, depending upon the density of the creeper. So you are shading your window envelope, or you're shading your wall. And because you're shading your wall, the surface temperature of the wall will remain low, and hence there would be a less of heat transfer. So that was one part of your question, where how to use it. And the second was still ventilated, right?
It was about daylight, sufficient daylight. Yeah.
Yeah, so it definitely will cut the daylight for sure. But if you have any other means to gain a daylight, then you should think about it. And again, as I see that, it's not that one thing will fit one thing you do and you are solving all the problems. Yeah, you are solving a problem of solar gains by putting a creeper, but then you must have some other strategy to gain more daylight. Either have a creeper on a south side, have a creeper on the east and west side, but don't put it on a north side. Anyway, north side, it will not grow also, because they will not get enough solar radiation. And get a daylight from north side, or get a daylight from the roof. There are multiple ways by which you can use creeper and still get a daylight.
Right. Thank you. Next question. So on slide 8, your matrix showed convection is different for wall, roof, and windows. Can you help us understand this difference with an example? So I think they're talking about the matrix. The matrix. Yeah. Yeah, this one.
Okay. So let's take one example of Yashima. Which one should we take? Wall, fenestration, or roof?
I think let's take fenestration.
Okay. So now, when you take a fenestration, what, as I mentioned, is a spatial decision is very important. Where are you putting your fenestration? Whether east side, north side, south side. So that's where it is red. Now, what is the material which you are using for fenestration? Like older days, are you having a wooden panes, or are you having glass? That also makes a huge difference in a heat transfer. So that's about conduction, right? Conduction, spatial, conduction, material. Now, convection and a spatial part along with the fenestration. This is where the operation of the building will come into the picture. If you are putting a fenestration which you want to operate, and if you are doing that with the prevailing wind conditions, just I need to take this call. Ouch, man. No. This is where if you are putting a fenestration towards a place where you're going to get more wind, that's where the spatial decision becomes very, very important. Materials and methods is not very important when it comes to a convection and a fenestration, because whether it is aluminum or it's a wood, through the convective current, through the convective heat transfer, that is not going to matter at all. So that's where the example where I'm connecting convection and a fenestration. Now, when it comes to radiation and a spatial part, again, it is orientation which will matter a lot. It will a number of windows and a size of windows, which also a spatial decision will matter a lot, and also glass, frame material. All of that will matter. Spatial also, where you have overhang, you don't have overhang, you have multiple overhang, you have horizontal overhang, you have vertical overhang. All that is a response towards the radiation and a fenestration together. So that's where probably I hope that little bit of connect is happening, but I can explore, I can explain more.
Yeah, I think the example we discussed now was good. Next question, could you suggest some literature for building thermal design, some books or to look at? That's one of the question.
I mean, I can share a list of books with the organizers, but I'm sure that you will have something with you. But probably for that, I can't really say upfront which books to be referred. And again, there are two kind of books which are available. One is which they explains the heat transfer principles. Then there are books which tells you the case studies of various buildings. But you might need to connect these two on your own, because there might not be any book where you say that heat transfer principles and case studies and some numbers put together. We are yet to reach to a level where we get these kind of books in India.
Right. Thank you. Next question. Which simulation tool has been used in the shown analysis estimates, and which software will be useful to model natural ventilation, that is convective heat transfer benefits? I think this question came in to around the next 2 or 3 slides. If you go beyond the next, beyond this slide.
So basically, let me tell you, I mean, direct answer is that we use Design Builder with Energy Plus as a Energy Plus with a Design Builder interface to carry out these work. So that's a direct question, direct answer. Same thing for natural ventilation. We do use Energy Plus. But more importantly, instead of which tool to be used, what is more important is how are you modeling it? Modeling and simulation, these are two separate domains. And if you are correctly modeling it, you are likely to get reasonable result, which is sort of acceptable or practical. But I would say sort of place some more efforts in modeling the tool. Now, why we use Energy Plus is because everything is pretty transparent, that it tells us that what equation does it use to calculate what. And you can look at the engineering reference, you can look at input-output reference and figure it out that how is it modeling, or sorry, how is it simulating whatever it is simulating. And that's where the preference is Design Builder Energy Plus.
Right. Next question. If we keep insulating material inside, does it affect the maintenance of the building material which is exposed? So be it inside or outside, how does the maintenance factor in here?
Most of the insulation material needs to be protected with the additional layer. Most of them. Although there are some materials available where, again, they cannot be used just 100% exposed. They need to be, there would be a screen on top of them. And that would become a protective layer. But otherwise, most of the insulation, whether inside or outside or exterior or interior, requires additional layer for protection. I hope that, or was it to deal with the aging of a insulation, or it is just a protection?
No, just maintenance, protection, yeah. Next, how is it different using insulating materials and materials with high thermal mass?
So as I mentioned, that insulation material will resist, or will reject rather, versus thermal mass will keep absorbing depending upon its specific heat, depending upon its capacity, but will not let you get the heat on other side. So thermal mass almost acts like a buffer, where let's say if you have how do I explain that in a high-speed trains, there are certain buffer zones which are supposed to get crashed. And if they get crashed, then and then people inside the bogies would be safe. So what they do is that they use this buffer zone to absorb the impact, versus Resistance is that upfront you start rejecting it. Up to what extent can you reject is depending upon the material. But the major difference, that's where I say that one is more like a raincoat, which is not allowing water drops to come in. Second is more like a Kumble, which is absorbing water depending upon its capacity, but not letting it get other side.
Right. Next, in a naturally ventilated building, which factor is more important, convection through fenestration or conduction through walls?
Both. But if I have to rephrase this, for a better answer, I will rephrase it is that what will matter a lot in which climate zone. So let's say naturally ventilated building in a hot and dry climate, I will put more emphasis on conduction. Because if I open a window, I'm going to get hot air. But if it is a warm and humid climate, I will put more importance on convection. Because anyway, my temperature is not going to go up so much. Right? In a warm and humid climate, you don't get a high diluted temperatures. So conduction is not so important, but through the convection, if I have to lose heat, that might help. And that too probably during early mornings and late evenings. So if I have to rephrase this question to answer, then I say that in which climate zone, which heat transfer principle will help, or which heat transfer principles should be looked at more importantly. I hope that answers the question.
Yeah. Next question, are there any downsides to incorporating a very high thermal mass? Does it become a liability if the mean temperature is greater than the comfortable temperature?
It is a liability. It will be liability, and it will be liability, especially in a composite climate or in a hot and dry climate. Once the thermal mass gets cooled down, it will really take a lot of time to raise its surface temperature or even the temperature. So that's what happens in places like Chandigarh or Delhi, where you have a thick wall. During the winter time, when this thick wall loses heat, then this rooms becomes very, very, very cold. Even outside temperature goes up, but inside temperature doesn't really go up because it's basically inertia. It takes a while for you to get an impact of what is happening outside. So one of the professor, Dr. Bansal, used to use one phrase very often, that all buildings are low pass filter. That means whatever happens outside in a naturally ventilated environment, it will happen inside eventually. But how long will it take is all depends upon what is your envelope characteristics. So thermal mass will become a liability if you are not managing it very well.
Right. Next question, which of the three heat flows is usually higher for a typical building in a warm, humid or hot and dry climate zone? So I think what they're asking is as a percentage of total heat flow, which has more contribution to play here?
I can't answer that. Because architecture, energy science or engineering is not simple math. A lot of things comes into the picture. So
right. Yeah.
Without looking at the case, it's difficult.
Right. Next question, can the entire building be made insulated from the outer heat, including the roof?
Yeah, you can do it.
Yeah.
You can do it, but whether you should do it or not is a question. And that I'll leave it to you. Otherwise, you can do it.
Yeah. Next question. How to take care of condensation while employing natural air circulation with radiative cooling by engineering design of the radiative cooling system, or are there other airflow control options?
No, you need to maintain at least 2 degrees higher than a dew point temperature, and with the natural means you can't really do that. So you will have to deploy some kind of mechanical means and control of that both.
Right. Next, so a dynamic facade which is climate responsive versus combination of fenestration, location and material, which has the potential to be more efficient?
Both. And none. Again, it's, I mean, I'm sorry, no, I think you really can't take a judgment on it, because each case needs to be looked at. And when you say dynamic facade, which is climate responsive, first of all, it's a little difficult for me to understand that. How can it be? But still, I mean, there cannot be a straight answer, sorry, at least not with me.
Right. Next, are there any affordable materials to replace glass in windows to avoid the humidity dome effect, which are affordable enough for EWS buildings?
Glass, humidity. No, what was it?
Yeah. So it's a little confusing, but are there any affordable materials to replace glass in windows to avoid humidity dome effect?
Anyway, so that humidity dome, these two words, if you remove it, is what, and if I rephrase it, that is there any affordable material to replace glass
Yes,
as a part of the window? I would say no. But glass is a cheap material. Glass is not very costly. If you use a single pane glass in affordable housing, the benefit of that is very, very high. Now, it is up to you to decide how do you want to put that window so that it doesn't really get a very high solar gains. Where is a location of the window or a shading on top of the window is what you're, but the kind of quality a glass can bring, vision from inside to outside, from outside to inside. I mean, although it's not a domain of this session, but the UV radiation which comes inside the building early morning through the glass, or in fact the daily spaces inside the EWS will have a far more advantage than placing glass with something else. And glass definitely is not an expensive material.
Right. Next question. Can you talk a little bit more about the graph shown on slide 14?
Yeah, so this is on a first vertical line, we have cases which is oriented on northwest southeast axis. So basically that particular building was oriented 45 degree, there are cardinal points. Then second case was longer axis was north south. Then again it was 45 degree cardinal, and then the building was oriented longer axis east west. So these are 4 cases. These 4 cases with another about 25 cases of window U value ranging from 1.1 to 2.5 at 0.1 degree, 0.1 watt per meter square increment. Third vertical line are 2 cases. In one case, you have a 0.3 horizontal overhang. In second case, you have 0.6 overhang. Then you have about another 10 or so cases where size of the window was varying from 1 to 2 or something like that. And then finally, you have a few cases for the RET. Each line makes one case and it was simulated. And some kind of energy performance index was derived. What we are showing you that, okay, if, or rather other way around, that finally what would be your RETV is in a fifth vertical line. That if you have east-west orientation, if you have a window U value of 2, if you have an overhang size of 0.3, and if your window size is 1.2, then you will achieve RETV of 50. So the fifth line is a result of first 4 parameter. And then there's a combination of it. I hope that explains. And there are a lot of internet resources available to generate these kind of graph, and there are some scripts also available out of Excel where you can do that. There are tools also which actually shows you very nice way of presenting. You might want to refer that.
Yep. Next question, how can we incorporate wood or less conductive materials in load-bearing walls as cutting cost on brick walls?
Come again?
So how can we incorporate wood or less conductive materials in a load-bearing wall to cut down on the cost of brick walls?
No,
I think
I wish to skip this. I did not get a question.
All right, sure, yeah. Okay, next question. How to put all of this information together and start our design process, keeping all these criterias in mind, and how to extract the useful things from all the studies that you have shown here today.
So easiest way is to start. Instead of thinking, how am I going to do it? Just simply start. Take 2 studies and say that I want to incorporate these 2 studies right now. Instead of incorporating 15 studies or 20 study or 30 study, don't do any of those. Say that 2 studies, I want to incorporate learning from these 2 studies in my case. Or instead of looking at U value, SHGC, VLT, thermal comfort, climate zone, you said, no, I forget it. Let me manage the insulation only. Today, 26th insulation, 27th VLT, 28th something else. You slice it down and then start bringing things together. You yourself will realize after 10 days that, oh, now I know how to integrate it.
Thank you, Professor Rawal. Next question, can you talk a little bit more on what is the difference between a trom wall and thermal mass?
No, I am still, so trom wall is a way of constructing a wall versus thermal mass is a character of a wall. Now, trom wall may not be, I don't know how to put it, but trom wall relies more on the solar radiation getting trapped at certain point, and then you extract that inside your indoor spaces with that warm air. If you have a wall which is, so let me try to explain you a little bit. So let's say you have a glass here, and then you have a brick wall. Can you see properly? No, let me, what I'll give me some charge.
I think Yeah. Yeah, no, a little bit on the, yeah, I think that's good.
So let's say you have a stone or a brick wall here. This is inside, this is outside. And if you are bringing some kind of solar radiation, making this cavity as warm, and then you are bringing that air, sorry, other way around, that air from this cavity to inside of the spaces, this warm air is likely to impact this thermal mass over a period of time. And this thermal mass may gain heat from the warm air which is moving here. So probably in the night, this thermal mass may help you to attain higher surface temperature when you do not have a solar radiation at your place. That's what I understand from this question, but I don't know whether I'm answering it or not.
Yeah, I think that's what was being asked in the question. And so we'll take a couple of more questions, Professor Rawal. And so the next question, what are the effects of ventilating the wall cavity?
Very important. If you don't ventilate these cavities, what will happen is over a period of time, the cavity will get saturated with a high temperature and it will lose its effectiveness. So a lot of people who make the cavity but do not make it ventilated cavity, what happens is that air inside over a period of time attain very high temperature. And then that will not have any kind of insulating impact. This is including those cooled which they put it on the rooftops. The cooled has very small air mass inside. And cooled is not the one which is sort of very insulating material. And if there is something on top of the cooled, again, cooled will not be able to exchange any kind of air with outside, and hence the inside of these coolers, the air will become saturated with the high air temperature, and then it will lose its effectiveness. So it may work for first 1 or 2 seasons at the most, but third season always it will lose its effectiveness. That's what my argument is. There would be a counter argument to this, but this is what I understand.
Right. And I think we'll take one more question here. And that's, so after analyzing the climatic zone and identifying basic passive design strategies, what are the next steps that you would suggest we should follow?
So, I mean, yes. So first, what you do is first you do a climate analysis. Most of the people which I have seen do climate analysis. Oh, temperature goes up, temperature goes down, wind comes from here, wind goes here, humidity this. How do you translate that into architecture or engineering is where you need to put some thoughts. Once you do that, you say that, okay, I have downsized my energy demand, or instead of 5,000 hours of uncomfortable hours, now because of these passive strategies, I have 200 to 300, 400, 500 uncomfortable hours. Now, depending upon what is the extent of this uncomfort, is this uncomfort because of the 35 degrees centigrade and 70% RH? Or this is uncomfortable because 42% and 95% RH. So even looking at the extent of uncomfortable situation, you pick up your mechanical system. And once you pick up mechanical system, you also try to spend some time in operation. Can you really make the operation of this mechanical system in conjunction with your envelope? That's how the reduction on energy consumption will take place. And then finally, renewables, as you know.
Right. And with that, we'll end the session here today. Thank you, Professor Rawal, for such an informative session. The Q&A was very helpful, and I hope that our participants can make the best use of the knowledge and practices that you shared with us today. I would also like to thank the Department of Science and Technology and all our sponsors and affiliates for their support. Lastly, thank you everyone for participating today. Goodbye and good luck. See you next week for the passive design webinar. Thank you all.
Wish you all the best.